Okay, here we go. This is where we put it all together. So far we've looked at what voltage is, we looked at what current is, we've looked at Ohm's law and resistance, we've looked at resistance in series circuits and parallel circuits, and we looked at Kirchhoff's laws. In today's lesson we're going to do what we call circuit analysis, and we're going to put all of those things in together, and the goal will be to determine what the voltage, determine what the voltage, current, and resistance are for all components in a circuit. So how can we go about doing this? Well, like I said before, we can use all the tools we have at our disposal. Ohm's law, where R is equal to V over I, or we rearrange this to say V is equal to I times R. We can use equivalent resistance. That is using the series and parallel formulas for resistance in order to take two resistors and combine them and as if they were just one resistor. We can use Kirchhoff's laws. And there's one for voltage, Kirchhoff's voltage law, and there's one for current, Kirchhoff's current law. So between all of these four things, Ohm's law, equivalent resistance, and both of Kirchhoff's laws, we should be able to determine a whole bunch of different quantities about circuits, even if we're only given a few. So an example might be a circuit like this. I have 5 different resistors. They're set up in a combination circuit, and we want to be able to fill in basically the chart on the right. So there are some things that we're obviously going to need to be given. We're told that the total or the voltage of the source here is 60 volts. And we're given the resistances in each resistor. Where this becomes in handy is to find out whether, for example, is the current going to get too high? If you have a maximum current that you can have through your wires, is it ever going to exceed that? Are we going to have certain components that have too much voltage or too little voltage? And so this is why we would want to be able to do an analysis of a circuit. All of our circuits are going to be relatively simple in the way that we're only going to look at one voltage source. Once we start adding multiple voltage sources in different combinations of parallel circuits, becomes quite a bit more complicated. If you got into electrical engineering, you would do something like that. You may see stuff like that in a first-year physics class as well. So, where do we start with this? Well, the first thing to look for, and it won't apply here, but the first thing you look for, are there any columns in my table? Are there any individual components that have 2 of V, I, or R? If they do, then you can use Ohm's law. And that doesn't apply here. So what can we start with? The only thing that I can see is trying to determine the equivalent resistance. And that will be the majority of work for this problem, actually. So the first thing we need to do is group resistors. And so find 2 resistors that are either completely in series or completely in parallel. Pause this if you can't identify where it is, where those 2 resistors are, and come back to it in a second. So the 2 resistors that we can group together are resistors 4 and 5. So they're in parallel with each other. 1 over R4, 5 is equal to 1 over R4 plus 1 over R5. So R4 is 30 ohms. So we have 1 over 30. R5 is 20 ohms plus 1 over 20. The common denominator is 60, which means I would have 2 over here, 2 over 60 plus 3 over 60 on that one, which gives 5 over 60. But remember, that's 1 over R45. So R45 is the reciprocal of that, 60 over 5, which gives you 12 ohms. So I can redraw my diagram, my circuit diagram. So a quick little sketch here. There's 1, 2, and back up. And then I've got 3, and the combination of 4 and 5. So 1, 2, 3, 4, 5. Now, we want to add 2 more resistors together. Again, if you can't identify them right away, pause, take a quick look at it, see what you think, which 2 resistors go together. And the resistors that go together are 3 and 4, 5. So over here on the left, those are in series, so we'd say R345 is equal to R3 plus R45. R3 was 10 ohms, R45 was 12 ohms, which gives us 22 ohms of resistance. And once again, don't try to cut corners, draw your diagram. It doesn't have to be really neat. You just have to have a very quick sketch. There's 1, there's 2, and down here we have 3, 4, 5. So we put more resistors together, and in this case, again, pause it and think about it if you don't have it right away. And the resistors that go together are 2 and 3, 4, 5. So 1 over R2, 3, 4, 5 is equal to 1 over R2 plus 1 over R3, 4, 5, because they are in parallel with each other. So R2 is, go back up to the top, 50 ohms. R3, 4, 5 is 22 ohms. Common denominator here, well, we're just going to go 50 times 22. There might be a lower one, but we don't need the lowest common denominator. We just need some common denominator that works. So to get 50 times 22, we'd have to multiply the 1 over 50 term by 22 on the top and the bottom, so that's going to give us 22 here. And the second term is going to have to be multiplied by 50 on top and the bottom, so that's going to give us 50 over here. So that gives us 72 on top and 1,100 on the bottom, which makes R2, 3, 4, 5 the reciprocal of that. So 1,100 divided by 72 gives you 15.3 ohms. So now we know, we draw this new circuit. There's 1, and then we have 2, 3, 4, 5, and they are in series with each other. So we can get the total resistance. Our total is equal to R1 plus R2, 3, 4, 5. R1 is 10 ohms. R2, 3, 4, 5 is 15.3, which gives us 25.3 ohms of total resistance. So let's go back up to the top and jot that down in here as 25.3 ohms of total resistance. And now it's going to start to get a little bit easier. Now we can see we have 2 numbers in one column. That's our total column, which allows us to get the total current. So we'll do that in red. The total current, using Ohm's law, is V, the total voltage, divided by the total resistance. That's just a rearrangement of the Ohm's law formula, which is 60 divided by 25.3, which gives us a current of 2.37 amps. Okay, so let's go back up here. 2.37 amps. So if we take a look at our circuit, we know there's 2.37 amps coming out of the terminal and 2.37 amps going towards resistor 1. There is no place for that 2.37 amps to go. It doesn't split anywhere in there. Therefore, we know that I1 must be equal to the total current as well. So, going back up, we can put in 2.37 amps of current there. Now again, we have a column with 2 of the three VI and R, so we can calculate what V1 is. V1 is equal to I1 times R1. I1 is 2.37, V1 is 10, which gives me 23.7 volts across resistor 1. Go back up, 23.7 volts. Okay, now where do we go? And this is where, without a lot of practice, we might lose a lot of people here. So ask yourself, can I use Ohm's law? No. Can I use equivalent resistance? Already done that. Nothing left, no resistance is left to calculate. So it's going to have to be either Kirchhoff's law, voltage law, or current law. And the current law works really well when you have two resistors that are in the same branch that have to have the same current, and we don't have that here. It also works really well when it splits up, and we know how much is in all but one of the branches, and we don't know that here either. So the only thing left is to use Kirchhoff's voltage law. The trick when using Kirchhoff's voltage law is to try to identify loops where you know all the voltages except for one. The simplest loop we have here, and I'll draw it in red on the inside, goes through 1, through 2, and then back excuse me, to the cell. And if we look at, we know the total voltage here, we know the voltage through 1, which means that we should be able to calculate the voltage through 2. So according to Kirchhoff's voltage law, the total voltage must be equal to the voltage through 1 plus the voltage through 2. That's that small loop that I just showed you. So 60 equals 23.7 plus V2, and when you do the math, V2 turns out to be 36.3 volts. Go back up here, 36.3 volts. So, what's next? We have Ohm's law that we can use because you have a V and an I. And come back down here. See, it's a lot of writing. It is a lot of little steps, and you have to take it one step at a time. This is a question that I would expect you to take 10 minutes or so, maybe even 15 on a test. So I is equal to V over R. And in this case, we're trying to get I2 because we know V2 and R2. V2 is 36.3. R2 is 50, which gives a current of approximately 36.3 divided by 50, and then we're going to round it to about 0.73 amps. We'll try to remain consistent with the decimal place that we have in our total current, which is the 100th place. So we'll use the 100th place over here as well. So 0.73 amps. Okay, well now we seem to be kind of stuck again. Can we use the voltage law? Remember, the voltage law we can only use if we have only one resistor that where we don't know the voltage. So if we look at the other loops here, I can draw another loop in green, going through 3 and 4, and then back. I don't know V3 and I don't know V4, so I can't use that. I can draw another loop here in blue, going through 3 and 5, and on the way back. And I don't know V3 and I don't know V5, so I can't use the voltage law. What I can do, however, is use the current law. We know that coming out of resistor 1, there is 2.37 amps current. We also know that 7.3 or 0.73 of that goes that way, which means the remainder will go this way. That's using the current law. So, according to the current law, from Kirchhoff's current law, we know that I1 has to be split up, and it goes through I2 on one path, and it will go through I3 in the other path. So 2.37 equals 0.73 plus I3, and when you solve for I3, you end up with 1.64 amps. So let's go back up to the top. 1.64 amps. We can also calculate V3, knowing that we can use Ohm's law, I3 times R3. So 1.64 times 10, nice easy calculation there, 16.4 volts. And we're back again to having to use one of the Kirchhoff's laws. And in this case, we know that the current is going to split up. And we have 1.64 amps current going through here between 3 and where it splits up to 4 and 5. But we don't know exactly how that's going to split up. So that doesn't help us. We need to use the voltage law again. And according to the voltage law, if we look at, say, that green loop, that dotted green line that I have there, if we look at that green loop, we can say that in total voltage, that's the voltage in, is equal to the voltage out. Now there's some voltage out in V1, and in the green loop there's some voltage out in V3, and there's also voltage out in V4. So this was 60. This was, V1 was 23.7. V3 we calculated to be 16.4. So whatever is left goes into V4. So V4 turns out to be 19.9 volts. You'll also notice that V3 plus V4 happens to be the same as V2. That's another way you could look at this. It's just another way of using the voltage law. So that's 19.9. Similarly, you could do exactly the same thing with the blue path over here and get the exact same voltage. It's the exact same process except you use V5 instead of V4. And then we could use Ohm's law for both. I'm going to skip through the calculations here just to save a little bit of time. We could use Ohm's law for both of these. 19.9 divided by 30 gives us about 0.66, and 19.9 divided by 20 gives us about 0.99, and we're done. As I mentioned before when looking at the Kirchhoff's laws, you should be able to identify whether you've done it correctly by your last step. So for example, we know that the current split up. So when you add between 4 and 5. So the current coming out of 3 split up between 4 and 5. If you add those two currents, 0.66 plus 0.99, you get 1.65 amps of current. Here, you have 1.64. Does that mean you did something wrong? No, they're essentially the same number. There were rounding errors. We started rounding right from our very first spot right there, and so there's always going to be rounding errors as you work through. If you were supposed to get 2.64 and you got 1.65, now that's an issue. That's not really a rounding error. But in this case, it worked out all right. So I want you to try something, and this one's a little bit different. Here's a circuit, and don't get fooled by the way that circuits are drawn. Look at it and ask yourself, are components in parallel or components in series? It doesn't matter whether I have a diamond type shape in this one or whether they were rectangular shapes. It really makes no difference. So all you have to do is ask yourself, are they in series or are they in parallel? And in this case, I'm given 4 of the resistances, I'm given the total voltage, and I'm given 1 current. And I don't want you to solve the entire circuit in this case. I've drawn the table so that you could. I would say this would be a kind of a high level 4 type of question if you were able to get all of the currents and voltages. I'm just asking you to figure out what the voltage drop is across resistor 5. So I'd like you to pause this right now, take an attempt at it. Don't come back and do the rest of this lesson. I'm going to do the answer for you in a second. Don't come back and do the rest of the lesson until you've had a shot, had an opportunity to give it a legitimate shot. If that means that you need to go and do some hitless questions and practice it a little bit more before you come back to this, then go ahead and do that. You can always come back to it some other day. If not, you can try it right now. It might take you 5-10 minutes, and come back and see how your answer is. So at this point, I'm going to go on and do the solution. So if you haven't yet done it, stop right here and come back to it later. So what we have here is kind of a mix of a bunch of stuff. We can't use equivalent resistance because we're missing too much stuff. We can't use Ohm's law for anything because we don't have any columns where we know 2 of the 3 voltage, current, and resistance. So we must be having to use the current or voltage laws. And this is what I want you to take a look at. Resistor 5 here has current coming in and current going out, same current, of 3 amps. Now, there is nowhere for that current to split until it gets to the source. So therefore, according to the current law, I total must be equal to I5. So they have the same current. So this is 3 amps. Now things start to maybe become a little bit more clear because we can use Ohm's law. So the resistance across the entire circuit is equal to the voltage for the entire circuit divided by the current through the entire circuit. So 117 divided by 3 gives you 39 ohms. So there's 39 ohms. Now that I have the total resistance, I can kind of work backwards from my equivalent resistance calculations in order to figure out what the resistance is in resistor 5. So before we do that, let's try to simplify this mess in the diamond on the left-hand side. So the first way I can do that is I can say that the R1 and R3 are in series with each other. So R13 is R1 plus R3. R1 is 10, R3 is 30, so that's 40 ohms of resistance. Similarly, R2 and R4 are in series with each other, so you would get 20 plus 40, which gives you 60 ohms of resistance. So now let's redraw that diagram. There's my voltage. And here I have R1 and 3, and here I have R2 and 4. And then there's resistor 5. So 1, 3, 2, 4, and there's 5. When I said don't get confused by the shape, that diamond shape, that's really just a parallel circuit. Those 2 and 4 are in parallel with 1 and 3. So you could redraw it in the way that I've drawn it down in the bottom. Now we can combine the rest of this stuff. Like we said, they were in parallel. So 1 over R1324 is equal to 1 over R13 plus 1 over R24. So 1 over 40 plus 1 over 60. An easy common denominator here is 120, which means that I have to multiply 1 over 40 by 3 on both sides, top and bottom. I need to multiply 1 over 60 by 2 on both sides, top and bottom. So that's going to give me 5 over 120. If you had trouble with the with the fractions, a lot of it is just practice. You're going to get better at them the more practice that you do. I'm going through quickly here. Feel free to pause it and think about it yourself and try to do your own calculations in the future before I go and calculate if you find it's going through too quickly. So R1324 is equal to the reciprocal of that, 120 over 5, which gives you 24 ohms. So if I redraw that, I have 1234 or 1324, whichever way you want to look at it, doesn't really matter. 1324, and then I've got 5, and that's my total. Well, I know that the total, RT, is equal to R1345 plus R5. Now, in this case, I said we were working backwards before because I already know the total resistance because I calculated it earlier, and it turned out to be 39 ohms. So 39 equals R1324, which is 24, plus R5, which means R5 is 15 ohms. So we go back to the top, and we put 15 ohms here for R5. We're one step away from our solution because we can use Ohm's law and say V5 is equal to I5 times R5, which gives you 15 times 3, or 45 volts. So 45 volts. Now the rest of it is quite tricky. There's a proportionality thing that goes into here. You can't really say, you know that 1 and 3 have to add up to 45, or 117 minus 45, and you know that 2 and 4 have to add up in a similar way, but you don't necessarily know exactly how they do that. You know the current needs to split up, but you don't necessarily know how they're going to do that. It is possible for you to figure it out. It's a little bit beyond what I would expect from this course, but if you're a 90 or high 90 type of student, then you should be able to figure that out. That's kind of the epitome of what a level 4, a high level 4 type of question actually is. So go ahead and try that. If you want to show me your solution later, I can give you some feedback and let you know whether you approached it correctly. And that is all she wrote for today.